Hello guys, welcome back to my channel Gamma Die Gamma. And in this video, after I think 2 videos of not doing math, I'm finally going to do math or calculus, because the last video was about linear algebra. And this integral is what I call the trial by fire. So let's get started. You'll see why it's called that. So as always, we have a problem before us. Let's call it I. That's defined as integral from 0 to infinity of the natural log of 1 plus 5 x squared, natural log of 1 plus 6 over 5x squared dx. Okay, so now if you have been watching my videos, you might suspect that this is some sort of Gauss's genius trick. But for a change, I'm not going to use that method for this video. Now, if you want to do this on your own, I'll give you a little hint. I want to parameterize this guy as integral from 0 to infinity, natural log of 1 plus ax squared, natural log of 1 plus b over x squared dx. That's the hint I've given you. And if you want to try that by yourself, please feel free to pause the video and then resume when you feel comfortable. Okay, I'm assuming by now you're just waiting for the solution because you hopefully tried this by yourself. So what I'm going to do is I'm going to differentiate both sides with respect to b, and it's a partial derivative because I is a multivariable function now of a and b. When I do that, this a natural log will be unchanged. I will have 1 plus b over x squared, and the numerator is as it is, and also an x squared term, because we'll have to basically divide or multiply by the coefficient that is apart from b. So anyways, this will be integral from 0 to infinity natural log of 1 plus ax squared divided by x squared plus b, and then the x squares will cancel out. That's the partial derivative with respect to b of I of a comma b. Now I would like to take another partial derivative, but this time with respect to a. So when I do that, now the denominator will not be affected. We'll have an x squared because that's the coefficient with a, and we'll have 1 plus ax squared, and we will have x squared plus b dx. Okay, and one important point to note is that if I had differentiated this function with respect to a first and then with respect to b, I would have ended up at the same thing, because since this integrand, the original integrand, this guy, is continuous on this interval from 0 to infinity. I mean, it's natural logs and they're continuous from 0 to infinity. We can use something that's called Clairaut's theorem in multivariable differentiation that says if you have function of x and y, partial derivative with respect to x first and then with respect to y of the function is same as saying partial with respect to, well, y first and then with respect to x of the same function, given that the function is continuous. So I'm just using this theorem, and you can see if you differentiate first with respect to a, then with respect to b, you'll get the same thing. Now the advantage of having such an expression or such an easy integral is that there are no natural logs and we can use partial fraction decomposition. So just for partial fraction decomposition, I would say let u equal x squared. So we want to end up, or our original term was u over 1 plus au and b plus u. We want to express this as a over 1 plus au, or rather let's say b first, plus a over u plus b. Cross multiply, we have u is equal to a times 1 plus au plus b times u plus small b. We have u times a times small a plus big B plus a times big B times small b. Now u is, the coefficient of u is 1, so a plus b is equal to 1, while this guy should be 0. You solve this equation simultaneously. You have b is equal to 1 over 1 minus ab. A is therefore negative b over 1 minus ab. Now we can plug this back into our partial with respect to a, partial with respect to b, I of ab, and I'm going to call this I prime of ab, although this is bad notation because it's a multivariable function, but we're differentiating with respect to both the variables, you know, one after the other. So sort of like a complete derivative, not really, but this is a bad notation, but I'm just using it for convenience. Our question now becomes b over ab minus 1 integral from 0 to infinity of dx over x squared plus b minus 1 over ab minus 1 integral from 0 to infinity of dx over 1 plus ax squared. Now the first integral isn't that hard, so we have b over ab minus 1 times 1 over square root b inverse tangent of x over square root b evaluated from 0 to infinity minus, I would like to plug out a from the denominator, integral from 0 to infinity dx over x squared plus 1 over a, which I will write as 1 over square root a, but the whole thing squared. Now the first guy, the inverse tangent of infinity is pi over 2, and at 0 it's 0. So we have pi over 2 square root b over ab minus 1 minus, calculating this guy, we get if I'm not wrong, 1 over ab minus 1 times square root a over a inverse tangent of x times square root a evaluated from 0 to infinity. So pi over 2 times square root of b over ab minus 1 minus, we will have pi over 2 because of the inverse tangent times 1 over ab minus 1 multiplied by the square root of a, and that's the I prime of ab, or partial derivative with respect to both variables one after the other. It's nice expression. Now what I'm going to do is we have to reverse everything, whatever we did. So first I will have to integrate with respect to a, because I mean, although we differentiated later with respect to a, let's integrate it first with respect to a. So partial with respect to a, partial with respect to b, I of ab. We will be indefinitely integrating with respect to a. And by the fundamental theorem of calculus, again with multivariable functions, the derivative with respect to a will basically just cancel off with this antiderivative. We have derivative with respect to b of I of ab plus some constant Okay, so let's look at this guy first. I mean, this was anyways I prime of AB, so we need to integrate this guy with respect to A first. Let's do that on a fresh page. Okay, so as promised, we have these two integrals with respect to A though. So when I calculate this, I have pi over 2 and I have a square root b. I have to divide by a b because I have the natural log of ab minus 1 minus, now I want to let square root of a equal t, so dA will be 2t dt pi over 2, and then I have 2t dt divided by bt squared minus 1, and square root of a is again like t, so the 2 goes off, the t goes off, and here we have pi over 2 square root b natural log of ab minus 1 minus pi over b. I want to take out a b from the denominator, dt over t squared minus 1 over square root of b, but the whole thing squared, because now we can use that formula for the inverse tangent on the second integral, minus, well, not the inverse tangent but the difference of logs, so pi over 2 times square root b natural log of t times square root b minus 1 divided by t times square root b plus 1. In case you're wondering how I got this, it's a standard result plus a constant of a, because we were integrating with respect to a. Okay, so now instead of the t, we have to go back to the a for the second expression. So if pi over 2 square root b natural log of square root ab minus 1 over square root ab plus 1 plus some constant of a. So now what we can do is we can just use a simple property that ab minus 1 using the difference of squares is square root of ab minus 1 multiplied with square root of ab plus 1, difference of squares simply. And then when we take natural log on both sides, we have natural log of a product which can be written as the sum of two different natural logs, pi over 2 square root b natural log of square root ab minus 1 minus pi over 2 square root b natural log of square root ab minus 1 plus, I'm using the natural log of quotient formula here, plus we have the constant. Well, all the negativity in our lives is just gone off now, so we have pi over square root b natural log of square root ab plus 1 plus the constant, and that is precisely our partial derivative of with respect to b of I of ab. And if we want to revert back to what that expression was, we had integral from 0 to infinity of natural log of 1 plus ax squared over x squared plus b dx. That was the expression of partial derivative with respect to b of I of ab. So now to find this constant of a, we need to take a as 0 because we integrated with respect to a, so we need to do something on a because b can be assumed to be a constant. So when we do that, we have natural log of 1 plus 0 natural log of 1, which is 0, entire integral goes to 0. And even over here, because this pi and over square root of b is a constant, natural log of 0 plus 1 natural log of 1 is 0, so the constant is 0. That means our expression for partial derivative with respect to b of I of AB is just whatever we got. So pi over square root b natural log of square root AB plus 1, and the constant was 0. And now to revert back to I of AB, that's what we wanted to find originally, we need to integrate not with respect to A but with respect to B now. So I'm going to do this integration on a fresh page, and on this side, after performing this integration, we'll have a constant of B like we had a constant of A, and we'll use a similar approach for that. So see you on a fresh page where I'll do the integration with respect to B. Okay, so as I promised, this is the expression that we need to find in order to get I of AB. Okay, now you might want to try some substitution, but believe me, that's not a good idea here. Let's try integration by parts instead, the good old integration by parts, where we will always differentiate the natural log expression. So make that u, because integrating natural log is is a really foolish error. Differentiating this guy, we have square root AB plus 1. It's always differentiating with respect to B. And we have a square root of A, I suppose, because square root of B, square root of A, because that was the constant, and then differentiating square root of B, we'll have a factor of 2 times square root of B in the denominator. And then if we assume dv over dB to be 1 over square root of B, then V will just be 2 times square root of B. So now using the formula for integration by parts, we have the pi is as it is, u times V. So 2 pi square root of B natural log of square root of AB plus 1 minus 2 pi, and then this guy times V, the du over dB times V in an integral of square root B square root A over square root AB plus 1, but that's still multiplied with 2 times square root of B. We have some cancelling factors, 2 pi square root B natural log of square root AB plus 1 minus pi times square root of A dB over square root of AB plus 1. Now I would like to introduce a substitution. Square root of AB is equal to W. I'm not writing the first bit, I'm just writing the second bit. Square root of A times pi 2W over A times W plus 1 dW, negative square root of A pi, we can pull the 2 out, and then A out. We'll have W plus 1 over W plus 1 dW minus 1. I'm adding and subtracting 1 in the numerator. So plus 2 pi square root A over A dW over W plus 1. So when I simplify, I have 2 pi over square root of A and just a W plus 2 pi over square root of A natural log of W plus 1. And I always had this other term along with it, I just didn't write it. 2 pi square root of B natural log of square root of AB plus 1. Now instead of W, I would like to reverse substitute the square root AB. So I get 2 pi square root b natural log of square root ab plus 1 minus 2 pi over square root a square root ab plus 2 pi over square root a natural log of square root ab plus 1. But as I promised, there is a constant of integration of b, and this expression is I of ab. We can just clean this up and group some terms. We'll have 2 pi square root ab plus 1 times natural log of square root ab plus 1 minus square root ab having a common denominator of square root a and this nasty constant of integration over here. Now I of ab, if I remember correctly, was integral from 0 to infinity natural log of 1 plus ax squared natural log of 1 plus b over x squared dx is just equal to this guy above. Now to find the constant of integration b, let's take b equals 0. We can't change a, is a constant. So taking b equals 0, natural log of 1 will make this entire thing go to 0. That means even this thing has to be equal to 0 for b equals 0. So putting b equals 0 here, we have 1. Natural log of 1 will make the product go to 0. And even over here we have a 0. 0 in the numerator. So 0 plus c of b is equal to 0, which means the constant is 0 again. That's the best part of having natural logs, like added, like additions in the arguments of natural logs and then multiplying together. That's the best part. That's why I can say I of ab is just this ghastly expression 2 pi times square root ab plus 1 natural log of square root ab plus 1 minus square root ab divided by square root a. Okay, really crazy result. And one thing I would have to point out that is that we first integrated with respect to a and with respect to b. We had this expression, we first integrated with respect to a and then with respect to b. The thing is, we can also interchange the order of integration. In a theorem that's analogous to Clairaut's theorem that's called Fubini's theorem. And this assumes that the function is continuous and the integral converges. All of these cases, things are valid in our case. We have I of ab. Now how does this compare with our original expression I, which was integral from 0 to infinity natural log of 1 plus phi x squared natural log of 1 plus 6 over phi x squared dx. Well, if you take a as 5 and b as 6 over 5, you can just plug that back into this guy to get I. Then using this formula, we have 2 pi times square root 6 plus 1 natural log of 1 plus square root 6 minus square root 6 divided by square root of 5, which has an approximate value of 5.119008, and this is being checked by me after I solved it using Wolfram Alpha. So there is no doubt of this being wrong. I hope you enjoyed this video, guys. This was a crazy trial by fire, double partial derivative and then double integration. Hope you enjoyed it. Hope you learned a lot. So please like, share and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Digamma in the math community. And in the meantime, stay home, stay safe, keep doing math. Don't get tired, don't overstudy, and peace out. Signing off.